The International Space Station contains a number of laboratories where science experiments are conducted. But it's important to remember that the station itself is a laboratory. It's a test bench where new technologies are being developed for use by NASA, but also by others in the future. One of those new technologies is called the Space Communications and Navigation Test Bed. That hardware has been out on the port side of the space station's truss structure, pointed up at the Tracking and Data Relay Satellite System satellites since July of 2012. And it's helping investigate how software-defined radio can support communications for NASA missions. The SCAN testbed experiment is run from the Telescience Support Center at NASA's Glenn Research Center in Cleveland. And the principal investigator is Richard Reinhart. Good morning, Rich. Nice to have you here this morning.
Good morning, Pat. Thank you.
Tell me about software-defined radio. How is that different than the radio that most of us are familiar with?
Well, if you think about a typical radio for a satellite, it will produce and receive signals transmitted over the air, obviously with the help of the antennas. Most traditional radios are developed to run one or maybe a few types of signaling formats, and they do that format for the life of the mission. And we would call that a hardware-based radio or a fixed radio.
It has one way to communicate.
One way to communicate with the ground station that it happens to be talking to, or if it relays through the TDRS network, like you mentioned at the introduction. All of those are the same waveform, the same signal for the life of the mission. It doesn't change. So, for example, a mission may do 1 megabit per second, which is the rate the data moves, with a certain modulation, a certain coding scheme, and a certain data format. But it does those kind of characteristics for the whole mission. A software-defined radio is different in that this signal is digitally implemented and programmed in software. So the functions that make up the signal are implemented in software.
Instead of the hardware.
Instead of the hardware. So these processing elements are more capable, they're able to do what NASA needs, and we're able to program everything in software.
And how does that improve the ability to communicate between station and ground, or to even to use different parts of the radio spectrum?
Well, what it allows us to do, because everything is in software, the software can be changed after the radio goes to space, and that's the new technology that we're investigating and trying to get experiences with so missions can use this more and more. This provides really unprecedented flexibility to future missions for new capabilities, to adjust to problems. If there's a problem in the communication system, maybe we can fix it in software, or we can accommodate new requirements either in the development cycle or after launch. It could be something we learn on Mars that we want to change what the software does once it investigates or learns something. So this reconfiguration, we call it, is really what the new capability is.
And you've been working at this for almost 2 years now. How's it been going so far?
It's been working great. Each of the software-defined radios, we have 3 on board, have over 1,000 hours of operational time. We get a lot of time because we have no crew interaction. As you mentioned, we operate the test bed from the Glenn Research Center here in Cleveland. But we're on almost every day running some type of experiment, either talking to the TDRS network or talking direct to ground. And so besides the hardware itself, these thousands of hours we have on the hardware, we're starting to develop the new software, these applications. And so as an example, if you buy a computer from Dell, you might have Dell create all the software you might ever run on that computer. And that would limit maybe what you could do. And so we're the same way. We want to be able, NASA wants to be able to develop new software for these radios. And so that's what we're in the process of doing now. We're learning how to develop the software on them and how to document everything we're doing so that missions can use these in the future.
I suspect that you find new kinds of software that you'd like to have and go to work developing as you implement this.
You do. You discover new capabilities, the processing capacity of the radios you can investigate, and really just new capabilities of what you can receive on orbit and what you can change.
You've, in fact, been able to utilize this to support other science experiments on the station, right?
We have. There's a couple of things between on station and within NASA's communications infrastructure, I would call it, the TDRS satellites. Because we're really the only Ka band system that NASA has talking to TDRS, and Ka band is a high frequency that NASA uses to communicate between satellites. So we operate at Ka band, and we checked out the two newest TDRS satellites that NASA launched. So last year we launched what was called TDRS-K, and this year we launched what was referred to as TDRS-L. And these are brand new satellites that NASA makes part of the infrastructure, and so we were used to test out those satellites, part of their acceptance tests. Another example is we worked with the Air Force to receive GPS signals from their newest satellites. Kind of a similar role where we're checking out these brand new satellites, but we believe we have the first space receiver for the newest frequency that GPS is offering. They call it L5. It's a particular frequency for GPS signals, different from what your car might receive.
I see.
But we do investigate how well those messages are sent from those satellites, and we feed back a lot of information to the Air Force. And finally, one of the experiments on station itself that we're doing, I mentioned that Ka band system that we checked out the TDRS satellites with.
Right.
We're using that system to investigate how much the truss of space station moves through a given orbit, either through the attitude changes or just the solar pressures, just how much that truss moves, and that'll help future experimenters that might install on the truss. And one of those is a potential optical communication system. You can think of our system as sort of a flashlight with our beam spreading as opposed to a laser pointer. And this is actually laser communications that might go up on station here in the future, but we're investigating that environment that optical system would see.
As a matter of fact, we're going to talk about that optical laser system tomorrow. But in terms of scan test bed, what can you characterize? What is the ultimate goal for this?
Besides checking out the hardware and these applications I mentioned, the software itself, what we want to do is be able to demonstrate what future missions, how they might use this technology. And so we want to develop a system that can recognize its environment and then use its resources in the most efficient way to get the most science data down. So that's sort of a big goal, but the idea is to recognize its environment. We want the radios to be able to change their data rate adaptively. We want them to recognize maybe there's an interferer or there's atmosphere between space and ground that needs to be accommodated for in this software. So we want the radio to actually change its own characteristics to accommodate the environment.
And you've still got some more time on orbit work to do, right?
That's right. The project is scheduled for another 2 years, and so we have a plan to develop these applications between the adaptive routing. We have some that deal with efficiently using spectrum, the frequencies that we operate at, intelligent routing. There's a lot of intelligence being added to the network so that we can, again, move more science data down.
Rich, thanks very much for helping explain what's going on here, and good luck with the remainder of the testing.
Well, great. Appreciate talking with you today. Thank you.
Richard Reinhart is the principal investigator for the scan testbed investigation now underway on board the International Space Station.